Good afternoon, my friends, and welcome back to another episode of Mastering Diagnostics with yours truly, Brandon Steckler, technical editor of Motor Age magazine. And today's topic of discussion is the importance of having a good ground reference. And when I'm talking about a ground reference, I'm talking about where we affix our ground point when we're using diagnostic tools like test lights and DVOMs and graphing multimeters and lab scopes, tools of that nature. See, the point of this video is to stress the fact that, like it or not, we as technicians are indeed scientists. And as scientists, it's our jobs, our responsibility to evaluate test results and to make decisions based upon those test results. So taking what we've learned over our years as technicians in the field, learning in the trenches, sometimes it's school of hard knocks, doing something incorrectly, deviating away from the service procedure and getting your butt kicked, or watching a fellow technician next to you complete a job in record time because he or she has found a way to do things a bit more efficient. Watching YouTube content like from our Motor Age channel, attending classes, acquiring fundamental basic knowledge. These things allow us to develop hypotheses as scientists, and these hypotheses will lead to the tests we perform. And the tests are truly questions that we ask, in this case, the car, the systems in that car, and more importantly, the components of those systems or the circuits in which those components reside, the virtual systems that allow these goals to be carried out. And to evaluate these test results are going to allow us to prove or disprove our theories, our hypotheses. So in the real world, what does that mean? It means leveraging our test results as stepping stones, carrying us closer to the root cause of the fault, the symptom that surfaces, the thing the customer is complaining about, and simultaneously allowing to step over unnecessary tests, unnecessary disassembly for visual inspection. Pulling the front cover off an engine and then going, oh man, I didn't find a problem. Now I got to put it all back together again and pursue my diagnostic approach one more time. So the tools that we leverage are going to allow this testing to commence. Meaning if we don't use the tools properly, we can't conduct the tests properly. And hey, many times we do use the tools properly, but the tools themselves are subpar. They're not capable. They're too slow. They can't react fast enough to show us the information we need in almost real time. So when I'm talking about tools, what good is it to measure the pressure in a circuit if the gauge you're using is inaccurate? What good is it trying to analyze NVH, noise, vibration, and harshness if the accelerometer you are using during that analysis is not affixed to a focal point? Even the components that reside on the vehicle have to be affixed appropriately. Consider an SRS control unit. The components internal to that device that are responsible for airbag inflator deployment rely heavily on the fact that the SRS control unit itself is fixed to a location because it allows the energy transfer, the inertia that takes place during rapid deceleration during an impact. These are inputs to the SRS control unit that are responsible for creating the deployment. And probably most applicable to this discussion today is regarding electricity. The tools we use to measure electricity. When we are measuring voltage, what are we really measuring? We're measuring the difference between what is being measured on, we'll call it the red test lead, and the black test lead. That pressure differential or indifference in voltage potential is what is going to be displayed on our device's screen, whether it's a graphing multimeter or a lab scope or a DVOM. If we don't have the correct reference point, the information we see on the screen does not truly reflect what is happening in the circuit being measured. And if we as scientists base our decisions on the test results, as we should, it's going to lead to an incorrect diagnosis, not because we didn't analyze the data correctly, but that the data is incorrect. It's not the truth. If I had a tape measure and I was attempting to measure something that was 1 foot in length, 12 inches, and I extended that tape measure to measure this, but I did not affix the tape measure to a fixed point, there's no way I could accurately span the tape measure to show the distance or the length of that item I'm trying to measure. It requires a fixed point, a point of reference, in order for that tape measure to be accurate. And going back to measuring pressure in a hydraulic system, or even in something like an intake manifold, it's all a matter of perspective. I'd be willing to bet money if I ask any one of you what 15 psi displayed on a pressure gauge truly means. Most of us would think it is 15 pounds per square inch positive. Well, that would be true if it was referenced to gauge pressure, meaning we are calling atmospheric pressure 0 psi. But if in fact atmospheric pressure is being measured as an absolute value, atmospheric pressure here where I live is nearly 15 pounds per square inch. So if I see 15 psi on an intake manifold pressure gauge, it could be an engine that is under full turbocharged boost, or it could in fact be an engine that isn't even running, and the pressure in the manifold is referencing atmospheric pressure as an absolute value. I'll give you another example, throttle angle. Or throttle position sensor circuit range can transition anywhere from 0 to 5 volts, but the actual operating range of the throttle sits within that range. In other words, it never fully goes to 0 volts, and it never fully goes to 5 volts. Said another way, relative throttle position is going to differ from absolute throttle position. Absolute throttle position might indicate 10% open when we were at closed throttle. And closed throttle would show 0% throttle angle, meaning it's resting and it's closed position, its minimum air rate. So again, it's all a matter of perspective, and we need to understand that when we are evaluating measurements or acquiring those measurements. When we're talking about measuring voltage, it's truly, as I mentioned earlier, a differential in electrical pressure or voltage. What we truly measure on the red meter lead and the black meter lead, the difference between those two measurements is what is displayed on the DVOM or lab scope screen. In other words, if I took both of my voltage leads from my meter and placed them both at the same exact point, it's no surprise that the DVOM is going to display 0 volts. It's not that there's 0 volts available at the point I'm measuring. If I'm at a 12 volt positive electrical potential and both meter leads are at that same location, the difference between the two is 0 volts. If I were to then move one of those meter leads to the negative side of the battery right at the post, we should show the difference in pressure to equal that of approximately source voltage. In other words, if I had a battery that was charged to 12.5 volts, we'll just round it down for discussion's sake. If I was reading 12.5 volts positive electrical potential at the red meter lead and 0 volts of electrical potential at the black meter lead, the difference between 12.5 and 0 is 12.5 volts. But more realistically, we encounter situations where there is poor connections or corrosion between battery ground and our measurement point, leading to voltage drops when current flows or a circuit operates. However, referencing your negative lead, in this case your black meter lead, to that location, our meter is still going to show us the difference in potential from the red to the black lead. However, it's not truly measuring ground. So even if we had a 12.5 volt differential in electrical pressure between the red battery terminal and the black battery terminal, our measuring device would not show that full potential and difference. It would show less. It would subtract the voltage drop across that poor connectivity that loose connection, that corroded connection. Something more visually appealing would be to analyze the brilliance of an incandescent test light. If we were to fix an incandescent test light across a 12.5 volt difference in potential, we should see that test light glow brilliantly. But again, introducing the fault just discussed earlier, where there's some voltage drop or corrosion between a negative battery cable's connection to the negative post at the battery, creating a voltage drop would reduce current flow and cause the brilliance of that test light to diminish. So rather than just talking about this, of course, I like to operate from the trenches. I want to show you in real life what happens when we reference our test equipment incorrectly and how it can affect our diagnoses. Again, even if we do everything right regarding analysis, if the information isn't captured correctly, it is not true. And if we make good decisions based upon bad information, the end result is the same, a misdiagnosis. So let's head out to the car. Today I'm going to be using my trusty Snap-on ZEUS, and we're going to display a couple of functions that the all-inclusive tool can do for us. We're going to be leveraging the ohm meter. We're going to be leveraging a voltmeter, and we are also going to be leveraging a single trace lab scope to demonstrate what I'm talking about regarding a poor reference to ground. Let's head outside.
So we're out here at the car and we're going to make our connections with our trusty Snap-on ZEUS. So the first thing we're going to do is connect our scope module. And what I want to show you here is I'm referencing the alternator pass-through bolt, which should be referenced to ground. And I've got my red test lead on battery ground. What we're going to do is connect our test leads and configure the tool to measure resistance. So our red meter lead is going to connect to channel 4, and our black meter lead is going to connect to channel 3. Next, we're going to configure the tool appropriately. So if we visit scope multimeter, and in this case we're going to select digital multimeter, we're going to select a resistance measurement for ohms. And as you can see, the value here exceeds what the tool is capable of measuring. Meaning in this case, and I know there's a glare from the sun, I apologize, we're more than mega ohm value, more than millions of ohms, referencing the ground leg at the alternator to battery negative. So at this point we're going to change the tool to reconfigure our Snap-on ZEUS to measure volts as in a digital volt ohm meter. And we're going to see how that affects the digital volt ohm meter's ability to display voltage available at the battery positive post. So we are simply going to back out. We're going to connect our tool now to measure voltage. What that means for us now is we are going to move our positive test lead to the positive battery cable. And we should expect to see source voltage if the difference between the positive voltage lead signal and the negative voltage lead signal are good. We should see source voltage. But as can be seen here, we are only showing 1.25, let's call it 1.3 volts. So let's think for a moment and understand the limitations of any tool you're using. We know a DVOM is going to display the difference in voltage potential between the red meter lead and the black meter lead. And when we went across the battery, we saw source voltage being about 2.56 volts, meaning the difference between the red meter lead and the black meter lead is 12.56 volts. We know that to be decent. However, when we referenced our ground cable our black meter lead to what should be a known good ground. Clearly it was not. And our tool, our DVOM from our Snap-on ZEUS, displayed just below 2 volts. So what does that truly mean? It means the difference between the positive or red meter lead and the black meter lead was only about 1.57 volts. Said another way, if we had 12.57 on the positive cable, which we did, and we have 11 volts at the area we tested with our black meter lead, it would show an indifference of only 1.57 volts. So what we are seeing is not a true representation of what the tool is capable of showing us or what this system is truly displaying. It's a poor ground reference, and that's the reason the tool in this case would let us down. The tool is working just fine and it's doing what it's supposed to do, but it's not referenced properly. And again, it goes back to the tape measure. If we don't place the tape measure in a fixed location, we can't display the difference between where that tool is located and where we are choosing to measure the distance to, simply because that point of reference is moving. Well, if our ground reference, our point of reference for our tool is not truly ground and it's elevated, our tool is only going to show the indifference between the red meter lead and in this case the black meter lead, being very, very little, less than 2 volts. So how would this display on a lab scope? A visual representation of voltage. Let's find out. So we're going to get a look at our scope now. And if you take a look again, pardon the glare, I'm going to go into volts DC. And I've got about 20 seconds of sweep time on the screen. And as you can see, we are just below 1 volt. So what that means is the difference between what the red meter lead is measuring at the battery and what the black meter lead is measuring at our ground reference is only a 1 volt difference. So what I'm going to do now is I'm going to change my ground reference point. I'm going to move the ground reference point from the alternator bracket back to battery ground, and we're going to see the difference in the line graph of how much it changes. Again, here's my ground reference. I don't want to move the alligator clip. I want to leave it where it is because I don't want to disturb my poor ground. We're going to take our other alligator clip and put it directly at the battery, and I'm simply going to move my meter lead from here to here. And we're going to watch the difference on the scope screen. So I'm moving it out here, and I'm going to put it right here. And look at the difference. We've gone from 0 volts, about 1 volt, up to 12. And I'm going to move it right back to our poor ground reference point. And look at all the noise. Look at the noise that showed up as I wiggled. Watch this. I'm going to wiggle this. What is that showing? Me wiggling this is showing a difference in ground potential. Technically a difference between what's measured here and what's measured here. When it's measuring closer to here, there's very little ground difference. Oops. There's very little ground difference. When it's measuring closer to ground, it's going to show nearly a 12 volt difference. So watch as I wiggle, wiggle, wiggle. Look at what it's doing to our scope. I've actually repaired the problem just there. I've wiggled it to the point that it works now.
So there's no magic behind this. It's simply understanding what the Snap-on ZEUS and its multiple functions, the DVOM, meaning the voltmeter and the ohmmeter, as well as the lab scope, can display for us. The tool performed flawlessly. However, it did give us information that was incorrect, and it had nothing to do at all with the performance of the tool. It was our connection to the vehicle. We simply had a poor ground reference. And as you could see, this led to lower amplitude signals. And if we were measuring available voltage rather than voltage drop, corrosion like this, voltage drop like this, would lead to elevated ground signals. In the case of a sensor signal that normally transitions from 5 volts to 0 volts and back to 5 volts again, call it a digital square wave. In the case of this speedometer here, Our perfectly good looking speed signal never truly made it to ground. And the reason being is due to the fact that we had a poor ground connection in the circuit itself. My scope was referenced to battery ground, or really good ground, and this allowed us to see elevated ground levels on the ground legs, the ground reference points of the circuits themselves. Like any tool or test we choose to implement, we always want to implement it on known good vehicles. And said another way, even after we prove that the tool functions and the test serves us well, we still need to verify the integrity of our tool before we implement it. So in the case when we are going to use our DVOM, or we are going to use our test light, or we are going to use our graphing multimeter or our lab scope, we need to first perform a test to prove the functionality of the tool. In other words, when I mention any one of those tools, the very first thing I'm going to do moments before I implement the tool in a live circuit test, a true test to determine the car's functionality, I'm going to place the tool across the battery. And if it's a test light, I expect it to glow bright if it's using all 12.5 volts, for instance. If it's a graphing multimeter or a lab scope, I expect it to display a line going left to right, indicating approximately 12.5 volts to show battery source voltage. And if it's a DVOM, I expect the display to show us a steady 12.5 volts. If I can do that, we've proven that the tool functions and that our test leads are good and everything's connected properly and everything is accurate. To summarize, I just want to reiterate that the tools are extremely important because they allow us to evaluate the components of the systems that carry out the goal and the circuits in which those components reside. If we don't use the tools correctly, the information that they do reveal to us is not the truth. And even if we make great decisions, if we do that based upon erroneous information, it will lead to a bad decision automatically. Referencing a good ground point is one of the most important things you can do in regards to electrical or electronic diagnosis. Proving out the tool works by placing it across a known value like a battery should show us full electrical potential. It indicates the tool is functioning. It indicates there's no open in any test leads and that the tool is accurate. I want to thank all of you again for joining me on this episode of Mastering Diagnostics. I'm Brandon Steckler, technical editor of Motor Age Magazine, and we will see you on the next one. Take care.